The last two topics I'd like to take a look at from chapter 18 would be the constant volume gas thermometer, and then of course phase diagrams. Here's a quick review of some common temperatures that are worth knowing. Body temperature, I think most of us are familiar with 98.6, which they've rounded to 99. Of course, that does depend on the time of day. I think when you wake up, your body temperature may be as low as close to 97. 37 is a good number to memorize for Celsius. And I don't really have this memorized. 310 kelvins is human body temperature. I just remember that we live in approximately 300 kelvins, whether it's body temperature, room temperature, or somewhere in between. 300 is a good number to have memorized. And we're going to see in a moment that to convert from Celsius to kelvins, you merely add 273. And that makes the boiling temperature easy to memorize because we know that water boils at 100 degrees Celsius. At least under normal circumstances, it boils at that temperature. So try to memorize some of these freezing temperatures as well. I don't have any of these memorized, but I suppose that well, I do have this one memorized. That's the easiest of all, right? And we'll look at that. Here is the constant volume gas thermometer. It could be as simple as a metal bulb with a fixed quantity of gas inside. There's no way for gas to exit or enter the bulb, and you've got a pressure gauge. And you would immerse this bulb filled with gas in something like a bath of ice water, which you know to be at 0 degrees, or you could immerse it in a quantity of boiling water, which you would know to be at 100 degrees. And the idea is, because normally when you bring two things into contact, if one is warmer than the other, the hot one will cool, the cool one will warm until they reach an equilibrium temperature in the middle. But if this quantity of fluid out on the outside here is much greater in mass, let's say, than the constant volume gas thermometer, then its temperature will change very little, and it's the quantity of gas that will eventually meet the temperature of the so-called reservoir. So the idea is this is large enough that its temperature is unchanged. This is the one whose temperature does the changing. So that's often called a temperature reservoir. And I believe we have a few of these in our stockroom, but unfortunately we won't be seeing those this semester for obvious reasons. And I should point out here, pressure gauge reading, absolute pressure. When you use a tire gauge to check the pressure in your automobile tires, for instance, if it says 35 PSI, the actual temperature within the tire is more like 50 PSI, because what the gauge is telling you is the air pressure above or over and above atmospheric temperature. The actual pressure within the tire would be the 35 PSI gauge pressure plus the 14 or 15 from the atmosphere. Here they're talking about an absolute pressure reading. Okay, if you were to immerse your constant volume gas thermometer into a bath of ice water, I've got a temperature axis here and a pressure axis here. If you did immerse it into a bath of ice water, you could be confident that the temperature of the ice water was 0 degrees Celsius, and given enough time, the gas within the thermometer would also reach that same temperature, 0 degrees. And because those particles of air or excuse me, I should say gas, because those particles of gas are bouncing around in here, exerting pressure on the walls of their container and pressure on whatever the mechanism is inside the gauge, you'll read a particular pressure off the dial. So there is a particular pressure associated with 0 degrees Celsius. That's one data point on the graph here. You could then remove the gas thermometer from the ice water bath, plunge it into boiling water at 100 degrees Celsius, and allow that system to reach equilibrium. So once the interior of the gas thermometer has also reached 100 degrees Celsius, obviously the pressure would have increased. And should we review why that's the case? Remember, it's very intuitive that pressure, absolute pressure, and absolute temperature should be proportional. And really, I haven't actually discussed the meaning of absolute temperature yet. In the last video, I talked about the proportionality between those two, pressure and temperature, without actually defining absolute temperature. So I should point out that the Celsius temperature is really not proportional to pressure. If you went from 0 degrees Celsius to 5 degrees Celsius, the ratio of those two temperatures is infinite, while the ratio of the associated pressures is certainly not infinite. So this only works on the absolute temperature scale. But remember, temperature is a measure of the average kinetic energy of these gas particles. Note the temperature here, 300 kelvins. The pressure is around 7 atmospheres. If I pump in some heat and allow the temperature to rise to close to 600 kelvins, then yes, the pressure does approximately double. So don't forget that absolute temperature and pressure are proportional. So there is a particular pressure associated with 100 degrees Celsius. And of course, that pressure is going to be higher. At 100 degrees Celsius, the gas particles within the bulb are zipping around faster. That means they crash into the walls of the container more often and with greater force. That translates to higher pressure. How do I go to the next slide here? This thing is stuck. Oops, okay. Well, you could also have prepared an even warmer environment. Practically speaking, off the top of my head, I don't know how you would do this, because if you try to increase the temperature of boiling water beyond 100 degrees Celsius, it doesn't work. You just boil more water, but the water that remains is still at 100 degrees. So let's not worry about the details. Maybe it's an oven that's been raised to 200 degrees Celsius, but now you immerse your constant volume gas thermometer into the 200 degree Celsius reservoir, and you would expect the pressure to go up. And do you note that the delta T from here to here is half of the delta T from here to here, right? Going from 0 to 100, that's half the temperature increase as going from 0 to 200. So we would also expect that the change in pressure from here to here would be half of the change in pressure from here to here. That is the meaning of proportionality. But hopefully you can see now that these 3 data points appear to fall on a line, and that's what we would expect for that proportional relationship. You could continue this experiment, and maybe you're thinking, wait a minute, the whole idea of using this constant volume gas thermometer is to create a thermometer. How do you know it's 200 degrees if you're in the process of calibrating the thermometer? Well, I suppose the idea is you've used some other type of thermometer to confirm that it's 200 degrees Celsius. And we're using that information to calibrate the constant volume gas thermometer. In any case, continue to take data. You would find that all of these points fall in a line. So here's just a reminder mathematically. We know from the ideal gas law that for constant volume and a fixed number of particles, pressure should be proportional to temperature. Put the V over here, and R over V, those are all just numbers. That would be your constant of proportionality. Absolute pressure is proportional to absolute temperature in that case. And then the interesting thing to observe, of course, is what's the meaning of this, this line intercepting the t-axis? Now, in practice, you cannot actually cool any gas down to this temperature and still have it be in the gas phase. Even nitrogen, for instance. I think most of the particles we breathe with each breath are nitrogen molecules. So the air is between 70 and 80% nitrogen. I forget the exact percentage. But if you cool nitrogen down to this part of the Celsius scale, it's going to condense into a liquid well before you get to this particular temperature. But suppose you could. Suppose that your gas really did behave like an ideal gas and it was still in the gaseous phase, even at temperatures way the heck over here. This line suggests that you would reach some sort of zero of pressure. Is that possible? What does it mean to have zero pressure? Does zero pressure even exist in the depths of interstellar space? Well, don't forget that pressure is the net result of all these microscopic or submicroscopic collisions between gas particles and the walls of their container. In order for that pressure to cease altogether, wouldn't there have to be no collisions, which would imply no motion on the part of these particles? So if you could bring them to an absolute stop, you might be able to expect zero pressure. We'll also recall that it's the average kinetic energy of these particles, which is signified by the temperature. So no motion would imply zero temperature, perhaps? And now you're getting a sense of the meaning of this temperature. Now, on the Celsius scale, it turns out that temperature corresponds to negative 273.15. Your book calls it negative 273 because many of the problems we do just involve 3 sig figs anyway. But if you want to be more precise, it happens at negative 273.15 degrees Celsius. But if that really is theoretically the temperature at which all motion ceases, it might be more meaningful to call that 0 degrees, because how do you get any colder than that? How do you get colder than things not moving at all? Well, if you go further into thermodynamics and statistical physics, you actually can assign a number to, or you can assign meaning to temperatures even lower than absolute zero, but we're not going to talk about that in this class so much. So the Kelvin scale is defined so that the 0 point is right here. For the Celsius scale, 0 corresponds to the temperature at which water would freeze at atmospheric pressure. But for the Kelvin scale, we put the 0 over here. So the Kelvin scale has the same size of a degree as the Celsius scale. An increase in Celsius temperature of 1 degree corresponds to an increase of 1 degree Kelvin increase, or they just call it 1 Kelvin. Remember, if the 1 degree Celsius increase on, or 1 degree increase on the Celsius scale corresponds to 1.8 degrees increase on the Fahrenheit scale. So Fahrenheit and Celsius, different size degrees, but Celsius and Kelvin, it's the same. And the remarkable thing is that this result does not depend on which gas you use. Suppose that the green gas is a constant volume gas thermometer that uses nitrogen, and this is hydrogen gas, oxygen. It doesn't matter which gas you use. When you extrapolate backwards, each one of these lines would pass through the same temperature on the Celsius scale. It's always negative 273, which is rather remarkable. And they have to agree, otherwise there's really no significance to that temperature, right? How could you say that negative 273 is absolute zero if using a different gas would give you a line that intercepted somewhere else? So they really need to all intercept at the same place. In fact, it doesn't even need to be a single gas. I believe you could mix oxygen, hydrogen, nitrogen all together. Of course, that would result in an explosion. You could mix non-volatile gases together, and you'd still find that the line intercepts at the same place to the extent that they behave as ideal gases. Now, while this is not a topic from chapter 18, it's worth pointing out now. There is something rather naive about this notion of absolute zero being the temperature at which all motion ceases. In the classical view, where we think of these gas particles as tiny little billiard balls zipping around in straight lines until they collide with another particle or collide with the walls of the container, in that view, the least possible energy one of these particles could have would be zero. And at the absolute zero temperature, each of these particles presumably would just be what? Floating there in space, not moving, or sitting on the floor of the container. That's kind of a silly picture, right? If you could cool this thing, all these little particles just drop to the floor and sit there, very well behaved. They don't move at all. And that model can take you pretty far. You can predict all sorts of things accurately when it comes to the behavior of gases, but it really falls apart when you get close enough to absolute zero. From the modern perspective, this is a perspective that evolved in the 19-teens, 1920s. It was discovered that the lowest possible energy for one of these particles is not zero. And it's very easy to understand that if you can accept the idea that each of these particles really behaves more like a wave than our the way we normally think about it. If you think of a gas particle like a baseball or a billiard ball, it's got a well-defined position and a well-defined velocity. You can talk about its trajectory, the path it takes through space. That's the classical picture. But as soon as you constrain that particle to occupying an extremely small volume, it really no longer makes sense to think of the particle in those terms. And you have to use so-called wave mechanics to describe the behavior of the particle. So just run with this idea for a moment. If each of those particles is like a standing wave within the box that it's forced to exist in, we've already looked at standing waves in chapter 17, and we know that there are a set of so-called modes, normal modes, allowable for standing waves. And the one with the longest wavelength would be the one such that half of a wavelength corresponds to the length of the box. And if we have time in this semester, we'll talk about how wavelength tells you something about the momentum of the particle. The longer the wavelength, the less the momentum, and correspondingly, the less energy the particle has. So this really would fix the so-called 0 point energy, the lowest possible energy the particle could have. And it's not zero. Hopefully we can come back to that later in the semester, but I'll just note briefly that the significance of this curve here, when we were talking about standing waves on a string, this was an actual profile of the vibrating string. When we were talking about standing acoustic waves within a musical instrument, for instance, the height of the curve represented the pressure amplitude, the oscillations of pressure around atmospheric pressure. Here we're talking about something very different. This ends up corresponding to the probability amplitude. So if you were to square each of these curves, the height of that squared curve would tell you about the likelihood of finding the particle at that position. So presumably right here, even when you square this function, the height of the curve would still be 0, and you could expect almost no probability of finding the particle right there at the midpoint of the box. Very mysterious behavior, at least to our classical sensibilities. Okay, moving on to phase changes. Here's a nice little cartoon picture illustrating the difference between the relationships between particles in the 3 most common phases of matter. I'm saying 3 because we're all familiar with solids, liquids, and gases. But you may have heard that if you get a gas hot enough, the electrons will be stripped from the nuclei of the gas atoms or gas molecules, and you would enter a 4th state of matter referred to as plasma. So these are really not the only 3 phases. You might want to do some Googling about superfluids, superconductors, Bose-Einstein condensates. These are other more exotic states of matter that we're unfamiliar with for the most part. In a gas, the particles are separated by distances considerably greater than let's say the diameter of the particles, and there's almost no interaction between them until they collide like hard spheres. The idea is when they're this far apart, there's no attraction or repulsion between them. They're isolated from each other. Here, they're close enough that approximation breaks down. There would be weak bonds between these, not strong enough to hold them together, but strong enough to prevent them from flying this far apart. So this is what we call a liquid. It flows. It does take on the shape of the container, but it does not fill the container the way a gas would. A gas spreads out and fills the container. And of course, a solid does not flow. Here, the particles are close enough that they're held together rigidly by their bonds, interatomic or intermolecular bonds. And if the arrangement of the particles is regular enough, it's referred to as a crystal. Okay, this is a graph you really want to be familiar with. The easiest example to think of would be the one we're most familiar with, water. Your book makes the point that while in common usage, the word water specifically means liquid water, in physics and chemistry, water really just refers to H2O. So solid water is what we commonly call ice. Liquid water is what we commonly just call water. And gaseous water is what we commonly call steam or water vapor. Okay, so I'd like you to consider a block of ice that's particularly cold. We often think, oh, well, ice, since water freezes at 32 degrees Fahrenheit or 0 degrees Celsius, ice must always be at 0 degrees. But even the ice in the freezer at your home, if you've got a freezer at home and there's ice inside it, that ice is colder than 0 degrees, considerably colder. So ice does not have to be 0 degrees. It could be negative 100 degrees Celsius and still look kind of the same. So suppose you start with a block of ice, which is at some temperature less than or colder than 0 degrees Celsius, and you put it over a flame. The first thing that will happen is that the solid ice warms up. It's still solid, so if you started out at negative 100 degrees Celsius, maybe the temperature will rise to negative 50. It's still solid ice. Eventually, you'll get that temperature up to 0 degrees Celsius, and then the temperature will no longer rise. So they've got a time axis here. The idea is you've got a flame of constant intensity, I'll call it. You're dumping the same quantity of heat per second into this quantity of water at all times. So, and maybe I should stick to the temperature that they've given here. It looks like negative 25 degrees Celsius. Eventually, the temperature of that block of ice gets to 0 degrees, but it does not rise any further. What begins to happen is a phase change. So during this time, there is a phase equilibrium between the solid and liquid phases of water. They coexist simultaneously. And I think we are to assume here that we're at atmospheric pressure. So they've drawn this box sealed, but just imagine a hole in it. So it's open to the atmosphere, and we know that the pressure that this system exists in is atmospheric pressure, 1 atm. Okay, so as you continue to dump heat into the system, or I really should say dump energy into the system, more and more of the solid water transitions into the liquid phase, but it's still a mixture of solid and liquid, and all of it is at the same temperature. In a moment, I'll try to convince you that that has to be the case. You don't get the water increasing above 0 degrees while the ice stays at 0 degrees. No, everything's at the same temperature until all of the solid water has been melted. Okay, once the entire block of ice has transitioned into the liquid phase, then the entire system, which is now all liquid, will start to rise in temperature. And we've all experienced that. We know what it's like to put a pot of water on the stove, hit it with the flame, and wait for it until it boils. Eventually, it will reach 100 degrees Celsius, provided you're at sea level. If you're at the top of a mountain, it will not actually reach that temperature. It will get to a slightly lower temperature and then boil. And what happens here is very similar to the transition from solid to liquid. During this time, you continue to dump energy into the system, but instead of the energy being used to raise the temperature of the particles, it's used for a phase change. So the liquid begins to transition into the gaseous phase. We call that steam. None of that water or steam will reach a temperature beyond 100 degrees Celsius until it's all been boiled. So the steam that's coming off of the water, it's at 100 degrees Celsius still. Even if you had this entire thing, like if you had flames all around so that you can imagine heating the water and heating the steam is still not going to rise in temperature. It will stay at 100 degrees Celsius until the rest of the liquid has been transformed or transitioned into the gaseous phase. So there's no increase in temperature beyond 100 degrees Celsius until all of the liquid has been evaporated. It's very similar to what I said previously about the solid to liquid transition. Okay, once the water has been completely evaporated, then if you had it enclosed still and you were subjecting it to heating, then you could superheat the steam. And superheated steam is really dangerous. I think some of the worst burns you could experience would be from superheated steam. Most of the time when we encounter steam, it's only at 100 degrees Celsius. Right. And any job where you're exposed to the risk of steam burns, that would be a risky job. Okay, let me try to convince you of what I said a moment ago, which is that the temperature of the melted ice, once the ice melts in the water, that water is not going to get any hotter than 0 degrees until all of the ice has melted. So let's try to just reach a contradiction here. Suppose the ice is still at 0 degrees and you've got some enormous flame beneath this quantity of ice and water. Suppose that the energy from the flame were used to raise the temperature of the water above 0 degrees. So let's say you've got the water up at 5 degrees Celsius, but the ice is still chilling, so to speak, at 0 degrees Celsius. Is that possible? Well, I think we all know that thermal energy, in common parlance, we say heat flows from hot to cold. We try to be more precise in physics because heat has a more specific meaning, I suppose, especially in chemistry. But we'll say that thermal energy flows from something that's at a higher temperature to something at a lower temperature. So if you did manage to heat the water above 0 degrees, as soon as it's at a higher temperature, it's going to give up energy to the 0 degree ice. And it doesn't wait for a 5 degree temperature difference to do that. As soon as the water is 1 degree higher than the ice, heat's going to flow back from the water to the ice. In fact, as soon as it's any temperature difference is the idea, the heat would flow from hot to cold. So there's no way to get the liquid any hotter than 0 degrees if it's still in contact with and in thermal equilibrium with the ice. You're going to have to heat the whole thing until it's at it. Well, you won't be able to raise the temperature of any of it beyond 0 degrees until all of it is in the liquid phase, and then you can raise the temperature. So it really comes down to that. Heat flows from a hotter substance to a colder substance. That means there's no way to get the water any hotter than 0 until you've finished melting the ice. That's not going to happen. And I think we're all familiar with this. When you drop ice cubes into a beverage to cool it, it's not as dramatic as holding it over a flame, but the ambient temperature of the room is, of course, higher than the water. That's the whole idea. You want to drink a cool beverage. So immediately you've got heat flowing from the air in the room into the water. But it's not like that has the effect of increasing the water temperature and not affecting the ice. Think how weird that would be if the heat flowing into the glass only raised the temperature of the water and didn't melt the ice. That means you could touch the ice, it would feel freezing, but the water could feel warm. That doesn't happen in practice. In fact, that would make this whole exercise useless. You couldn't cool your beverage by dropping ice cubes into it if the heat flowing in from the outside could raise the temperature of the water without melting the ice. Then you would just have warm water with cold ice cubes in it. What's the point of that? So let me backtrack for a second. Suppose that when you took these ice cubes out of the freezer, and I don't actually know the temperature, let's say it's negative 10 degrees Fahrenheit. Those ice cubes aren't going to melt until they get all the way up to 32 degrees Fahrenheit. That's the fusion or melting temperature. So let's just suppose that these ice cubes are so cold, they're at negative 10 degrees Fahrenheit, that when you dump them into the water, the warm water, which let's say was at room temperature, it cools down and the ice cubes warm up, but that the whole system reaches some equilibrium temperature of, let's go with 20 degrees Fahrenheit. So the ice cubes are so cold and you had enough of them that when you throw them into the warm room temperature water, the whole system reaches an equilibrium temperature of 20 degrees Fahrenheit. That doesn't work, does it? Because if the water was at 20 degrees Fahrenheit, wouldn't it also be frozen? You'd have one giant ice cube. And that doesn't happen either, does it? You don't throw ice cubes into a glass of water and then the whole thing freezes. Okay, so I picked bad numbers. Let's just suppose that the whole thing is at 32 degrees Fahrenheit. It would have to work out that way. So this is a mixture of solid water and liquid water at an equilibrium temperature of 32 degrees. We're in phase equilibrium here. It is possible for, it's like you can go back and forth. It's kind of like if you went up to Niagara Falls, you went to the border of Canada and the United States, you had 1 foot in Canada and 1 foot in the States. You're just straddling that line, the boundary between the two. Here we're straddling the boundary between the liquid and solid phases. It's possible for liquid water and ice to coexist at 32 degrees. Okay, but as the minutes go on and more heat enters from the environment, the warm air of the room, more and more of the ice will melt. Once it's all melted, for a moment, you've just got a big glass of water at 32 degrees. That's still cold water, but from there on, the whole thing will rise in temperature back towards room temperature. All right, the behavior of dry ice, which is really solid carbon dioxide at atmospheric temperature, that behavior is much less familiar to us than the behavior of water. I don't think all of us have interacted with dry ice. I don't think you could just buy it from your local grocery store. And one reason for that is it's dangerous. If you leave a chunk of it in your hand, you can easily burn your hand. I say burn, but of course it's like a cold burn. You could damage the tissue of your skin if you leave it on there too long. And I think there's other dangers as well. I saw a headline in the news not so long ago about some party, was it Russia? They threw a bunch of dry ice into a pool to cool it down, and there were some fatalities. I don't know if it was because of excessively cold temperatures, probably not. It was probably more about suffocation because you can't inhale solid carbon dioxide. Well, the strange thing about carbon dioxide at normal atmospheric pressures, if you take that chunk of dry ice, as it's called, and just set it on the ground and watch it, it goes straight from the solid phase to the gaseous phase. You'll see what looks like steam coming off of it. Of course, that's gaseous carbon dioxide. It's probably still very cold. I don't think you'd want to inhale that. You can breathe the carbon dioxide from a 2-liter soda bottle. After you've poured out all the liquid, there's still some CO2 sitting in there, and you can inhale that. It's not going to hurt you because it's warm, but this would still be very cold. And it just completely skips the liquid phase. You don't see a puddle or little drops of liquid CO2 running down. It just doesn't happen. It can happen, but not here on Earth under normal circumstances. So let's look at why. If you went to the surface of Venus, I didn't label this, but I pulled up a stock image of the surface of Venus, and you threw a chunk of dry ice down on the surface. I believe, I checked the numbers, you actually could see it melt into a puddle of liquid CO2. I have no idea what liquid CO2 looks like. That must be a novel experience to look at that. And I've drawn some very long arrows signifying the increased atmospheric pressure on the surface of Venus. It's considerably greater there. In fact, I think it's almost 100 times greater. That's just a gnarly statistic. It's the planet closest to us. Every night right now, you can look off to the west. After the sun goes down, you can see Venus glowing very brightly in the western horizon. The diameter of that planet is nearly the same as Earth's. A lot of things are similar, but the atmosphere is much different, something like 100 times the pressure. And so under those circumstances, CO2 actually can flow as a liquid. Contrast that with planet Earth. Here's a picture of the desert, where the atmospheric pressure is much lower. It's not high enough to squish those particles together and keep them in the liquid form. Now you may be thinking, well, how is the atmospheric pressure strong enough to squish it together into solid form if it can't keep it in the liquid form? And I don't have an answer to that, but that's one way to kind of think about it, is that if you could subject, as you increase the temperature of this substance, CO2, the particles within the substance are going to be jiggling around faster, jiggling around faster. when you raise them to a certain temperature, they have a tendency to break free from each other. Once they've started to break free, here on Earth, the pressure from the atmosphere is not enough to keep them close enough that they're in a liquid phase. They just go straight to gas. That's sort of how I think about it. Obviously, the real physics explanation will be more sophisticated. But if you could take that same chunk of dry ice, put it on Venus, you might see the liquid phase. If you got it hot enough, eventually it would go to the gaseous phase as well. Of course it would, because I'm sure there's lots of CO2 in the atmosphere of Venus. So to really make sense of that, you need what's called a phase diagram. And I mentioned in a previous video, these are not particularly intuitive. We're not born knowing any of this stuff, so you should really spend some time reading about them in the chapter and studying them graphically. Okay, so this is the phase diagram for carbon dioxide. We've got a pressure axis and a temperature axis. Let's talk first about conditions here on planet Earth. At sea level, the pressure is 1 atmosphere. So suppose you had a brick of carbon dioxide that was way down here at something like -100 degrees Celsius. So we've got our horizontal and vertical coordinates here. At 1 atmosphere of pressure, that's the vertical coordinate, and -100 degrees Celsius, I'm just guessing that temperature, evidently carbon dioxide would be in the solid phase. You wouldn't see steam coming off of it. I say steam, but that's really gaseous water. You wouldn't see carbon dioxide vapor coming off of that brick. It would just be a solid brick. But what happens immediately when you take some dry ice home from the store or wherever you buy that stuff, and you set it on the stage of your high school theater buildings, to make the fake smoke or whatever, doesn't the exterior of that brick immediately start to warm until it meets the temperature of the ambient air? And immediately heat is exchanged between the air of the room and the exterior of that brick. The core of the brick is going to warm last. In fact, there's probably a temperature gradient from core to surface of that brick. So at the very core, maybe it's still -100 degrees Celsius, and the skin of the brick will immediately approach room temperature. And that means that the skin of the brick is going to be moving this way. It's still under 1 atmosphere of pressure because it's exposed to the atmosphere. But the temperature of the exterior, the surface of that brick, will immediately start to rise. And when it gets to right about here, then we've got the so-called phase equilibrium. That is when the exterior of your brick can be simultaneously in 2 phases. You see the solid beneath the surface, and you see the surface immediately transforming into a gas. So the possible values of pressure and temperature which produce liquid CO2, those are out of reach because we're still down here at 1 atmosphere. So right here is where it sublimates. As the temperature increases from below -78 degrees Celsius to above -78 degrees Celsius, the carbon dioxide sublimates. And that's what you are seeing when you use dry ice. If you're at a performance where they're using dry ice, you're witnessing the phase equilibrium right here. I'm not going to talk in this video about critical point and triple point. I might mention triple point for water. But let's go, so this horizontal red line could represent the warming that I was just speaking of. You're always at 1 atmosphere. Now, if you put this carbon dioxide into some sort of beaker or pressurized chamber, then you could be up here somewhere else. I'm just imagining that it's sitting there open to the atmosphere. Let's take ourselves to Venus now. I mentioned that the atmospheric pressure on Venus is something like 100 times as great. So you'll see this is not to scale, 1 to 5, 5 to 73. This is just schematic here. But let's suppose that this is the pressure on Venus. And actually that's well above the so-called critical point. But if you've got a brick of dry ice, again, down at -100 degrees Celsius, and you throw it into the Venusian, isn't that a cool word, into the Venusian atmosphere and allow it to immediately warm, the outside of the brick is going to warm up until it reaches this point, And that is when it would begin to transition from the solid phase into the liquid phase. Presumably, the core of your brick would still be colder, but the surface of the brick would eventually reach this temperature, and there would be a phase equilibrium between liquid and solid. You'd have a brick of CO2 immersed in a puddle of liquid CO2, much like an ice cube in a puddle of 32 degree Fahrenheit water here on the surface of the Earth. Eventually, all of the brick would have melted into the liquid phase, and then it would continue to warm even further. Okay, there's a very similar contrast we can look at. Let's go back to talking about water, not carbon dioxide. We're talking about dihydrogen oxide, if you want to call it that. And under normal circumstances, in Long Beach, we're near sea level. The atmospheric pressure is 1 atmosphere. So if you start with a chunk of frozen water, solid water, we call that ice. Let's say you've taken it out of the freezer, so it's colder than 0 degrees. Maybe it's down here at negative 10 degrees Celsius. So right here, this would be the state of your brick of frozen water. But the surface of that ice cube will immediately begin to rise in temperature. It's still at atmospheric pressure, but it will rise in temperature because it's exposed to the ambient air. And eventually, it will reach 0 degrees. The core of your ice cube is still at a temperature less than 0 degrees because it takes a while for that heat to diffuse, so to speak, down to the core. But now you've got phase equilibrium between solid and liquid. Your ice cube is sitting in a puddle of cold water at 0 degrees Celsius. Eventually, the entire cube will have melted, and that 0 degree water will sit there in your room and gradually get warmer and warmer until it reaches room temperature, which is, what do we say? Something like 20 degrees Celsius. So it'll just hang out here. This would be your liquid water just sitting in a puddle at 20 degrees. Now, if you had poured that water into a pot and set it over an open flame on your stove, now the water is going to rise in temperature. It's still at 1 atmosphere of pressure until it gets to 100 degrees. Then it will begin its phase transition. So it's at another phase equilibrium, this time between liquid and gas, and it will stay at that temperature until all of the liquid has boiled. And at that point, you're just going to have a bunch of gas at 100 degrees Celsius. Right? You can't get it any hotter than that because it's no longer contained. It's escaped from your pot. At that point, it would actually just cool back down. Okay, so what happens if instead of cooking or boiling this water in Long Beach at sea level, what if you went to the top of Mount Everest? I will never be at the top of Mount Everest because I've read that people who do that, when they come back down, their reflexes have slowed down. They often have permanent, even if it's mild, permanent cognitive changes. Not worth it, man. I get this human impulse, why did you climb the mountain? Because it was there. I get that. But it just so happens that the tallest mountain on this planet is 30,000 feet? What if it was 50,000? Are you going to climb that too? What if there was a mountain on this planet that's 100,000? And when you go to the top and come back down, you're brain dead for the rest of your life. Are you still going to climb it? I don't know. There's got to be some point at which it's not worth it. And for me, that's like 5,000 feet. Okay, I did go to the top of Mount Baldy one time, but no permanent damage there. You know what tastes really good after you go to the top of Mount Baldy? If you've hiked, let's say 6,000 feet, go to In-N-Out and get a chocolate shake with your burger. There's nothing like it. That burger will never taste that good. Okay, so if you're at the top of a mountain now, I suppose we'll talk about this more as we get into subsequent chapters, but the atmospheric pressure is considerably lower at the top of Mount Everest. This is exaggerated. It wouldn't be this much lower. Notice that this is not to scale anyway. But if you've got your pot of water at, let's say, 20 degrees Celsius, 68 degrees Fahrenheit, so you're right here on the PT diagram, the phase diagram, and you put your pot of water over an open flame, your pot is still exposed to the atmosphere. You're not in a pressure, it's not in a pressure cooker. So it's going to remain at this pressure, whatever that pressure is. Maybe it's 75% of 1 atmosphere. And the temperature will rise until you get here. This is the, I think they call this a phase transition curve or phase equilibrium curve. Here's when it will begin transitioning to a gas. And you'll notice if you drop a perpendicular down to the t-axis, this temperature is lower than 100 degrees. So it has to do with where this horizontal constant pressure line intercepts the phase equilibrium curve between liquid and gas. And again, this is exaggerated. This looks like it's down here at 50 degrees Celsius. It's probably more like 98, 99. But the point is your water will begin to transition from liquid to gas at a temperature lower than 100 degrees. And that means if you cook something in that boiling water, you will be cooking it at a temperature less than 100 degrees. So if it takes 10 minutes, I can't even think off the top of my head, what would you be cooking at the top of a mountain? Raw beef? No, why would you take raw beef up to the top of a mountain? Vegetables? Okay. I try to avoid those personally, but maybe you've got some, you're gonna blanch some broccoli. Do you do that to broccoli? I would just bury it in Velveeta first, or like tempura, whatever. But if you would normally boil your broccoli for 5 minutes, that's probably way too much anyway. You can tell how unfamiliar I am with boiling broccoli. But if you would normally boil it for 5 minutes, you're gonna have to boil it for longer because it's being boiled at a lower temperature. You know, whatever chemical change it needs to undergo to give it that cooked structure, that takes a certain amount of energy, let's say, to do that. Well, if you're cooking it at a lower temperature, you're putting in less energy per second. So you'll have to use more seconds to affect the same change. Okay. Let's do the other extreme now. Instead of cooking on a mountaintop where the pressure is lower than normal atmospheric pressure, let's suppose that you are now cooking your food in a pressure cooker. I've never used a pressure cooker. I know some chefs swear by them and say they should have started using a pressure cooker early in life, but it just sounds dangerous to me. I would be nervous around a pressure cooker. It just sounds like a pressure cooker type situation. Again, this is not to scale. This is exaggerated. I don't know what a typical pressure is inside a pressure cooker, but let's say it's significantly above 1 atmosphere, because you've got the food and the water sealed. It's not open to the atmosphere. You can develop pressures well above 1 atmosphere. Let's look at where this line intersects the equilibrium curve between liquid and water. So if you've got your pea soup and your ham hock or bacon, whatever you've got in your pressure cooker, and you turn it on, and I guess they're mostly electrical pressure cookers, the temperature's going up and up and up and up and up at some high pressure, and eventually the temperature of the water reaches a point where it's now about to a phase transition. The water within the pressure cooker begins to boil, but look at where that intersection happens. Drop a perpendicular. That's at a temperature well above 100 degrees. So again, it's all about where the constant pressure horizontal line intercepts the phase equilibrium curve. Now, truthfully, this situation is a little more complicated because on the mountaintop, the pressure is at a fixed value. That's the pressure of the atmosphere at that altitude. That's fixed. You don't have any control over that. But within the pressure cooker, the more water gets evaporated, the higher that pressure would be. So that's actually not a static value. The discussion would be a little more complicated. But the basic fact remains the same. The water is going to boil somewhere over here on the phase equilibrium curve, not down here. And that's how you can develop higher temperatures. You can cook food quicker. Now, I'm assuming the food's going to come out a little differently if it's been cooked quicker. I mean, there's a huge difference between pizza reheated in a microwave and pizza reheated in a toaster oven. It comes out all soggy in the microwave, and I'll still eat it. I'll never say no to pizza. I'll go to Chuck E. Cheese's and gladly accept that pizza. There's some frozen pizzas I just can't eat. They're just too disgusting, too salty. But for the most part, I never say no to pizza, especially if it's free. I just pulled up a graphic here of a typical steam or a pressure cooker. What are they telling us? Okay, 250 degrees. So that's a rather modest increase in temperature. We haven't moved very far up the equilibrium, the phase equilibrium curve between liquid and gas. So the pressure is probably not that much greater than 1 atmosphere. Do they even tell us in here what that pressure is? No, because most of us don't care about pressure when we're in the kitchen. Okay, so one last example here. I believe I pulled up the phase diagram for methane, or as, is it Australians or Brits who call it methane? That sounds funny to me. But here's the phase diagram for methane. And first, let's examine where we would be on the surface of planet Earth. Okay, 1 atmosphere of pressure and a temperature of 20 degrees. So not number 2 here. I'm not going by these numbers here. This is just a diagram I pulled up. I think on the surface of planet Earth, we're right about here on the PET diagram. And it's very clear that methane would be a gas. Right? Well, we kind of know that, right? Because the gas that comes out of your intestines, I think, has a large methane component. I think you burp it out too. Cows burp it out. They say that cow burps contribute significantly to global warming. I've been trying to learn some group theory recently. That's a branch of math that has a lot of applications in physical science. And I've looked at the symmetry properties of the methane molecule. I believe it's one of those tetrahedral molecules. It's perfect little tetrahedron with all these symmetries. It's kind of odd to think that when cows burp out methane, or if you want to switch over to the bathroom humor here, that you're expelling what, 10 to the 23rd of these perfect little tetrahedra. How could something so crude at the same time be so mathematically beautiful? Strange contrast there. In any case, methane on planet Earth at atmospheric pressure and normal temperatures is a gas. But on the surface of Titan, which is the largest moon of Saturn, you can see Titan through a big telescope. It just looks like a little dot orbiting Saturn. Well, you don't see it orbiting. You'd have to wait many hours to notice the orbital motion. But the atmospheric pressure on Titan is almost 1.5 atmospheres. So we're a little higher than here, maybe up here. That's not a huge difference, but the big difference is the temperature. It's extremely cold on Titan because Titan does not have the type of atmosphere we have, and Titan is also way further from the sun than we are. So the surface of Titan is right about here on the PT diagram, squarely in the liquid portion of the phase diagram. So it's possible for methane to flow in rivers of liquid methane. How exotic and cool is that? I mean, you wouldn't want to go there without like a really sophisticated spacesuit. You'd freeze immediately. But if you could go there in a little special cocoon of a spacesuit that keeps your body warm and regulates the atmospheric, or regulates pressure within your helmet, that would be pretty awesome to walk around and experience that. Not only might there be rivers of methane, but I even read that rain can fall. It can precipitate. And I forget why, but the droplets would be much bigger than water droplets. And because the gravity is considerably weaker on Titan, they would fall more slowly. So that's really cool to imagine, walking around on the surface of this moon with these giant raindrops of liquid methane falling very slowly. Just an extremely exotic mental picture there. So here's an artist's rendering of what it might be like to walk the surface of Titan. And presumably you've got methane raining down. You've got these little rivers. Okay, I'll leave you to wallow in your reverie now as you contemplate life or the absence of life on Titan, the largest moon of Saturn. But just be aware that in our lives, we occupy a rather small portion of these phase diagrams. So we're not familiar with all of the extreme behavior of the various substances we encounter. And even this is very limited compared to what does exist in the universe. If you examine the behavior of substances or the conditions at the core of a star, the pressures you're talking about are way off the scale, just way off the screen, not even close. Same with the temperatures. So things get even stranger. You're not even talking about solid, liquid, gas. You're talking about plasma, things beyond plasma. I don't know. There's a whole branch of physics called plasma physics. The more you learn, the more weird it gets, the weirder it gets. Like at the core of Jupiter, I think, they think the hydrogen, on this planet, hydrogen exists as a gas. But at the core of Jupiter, it's under so much pressure, I think it behaves like a metal. It takes on metallic properties. So I'll let you read about that to your heart's